Hello and welcome to my presentation at this Altair workshop, and many thanks for your interest into my or to our work. My name is Simon Hillebrand and I'm a part of the former student team Ecurie from the RWTH Aachen, and I'm the former group leader of the chassis group in our team. Today I can present you some impressions of our work we have done in the past year related to the Altair software. A short overview: what is Formula Student? Formula Student is the largest student design competition in the world and founded in the USA. Currently we have over 600 teams from universities and college all over the world. And they're built and they construct and build every year a new one-seater race car, as you can see on the picture on the right side. And then competitive in several disciplines against the other universities. Then there's the Formula Student Germany, the FSG. It's the biggest event in Europe. Nearly 70 teams take part in different classes, and there's there's 1 week in Hockenheim where the races take place, and also the FSG writes our regulations for the season. To get a short overview what I'm talking about, in the beginning I want to introduce you into our team. Then I give you an overview about our last season and about the success we get. And then I want to talk about the Altair software we use. And in the end, I will give you an overview about the highlights in our current cars, which are related to the use of the Altair software. Especially the chassis or topology optimization and the structural aerodynamics simulation. Here you can see the team from the season 2020-2021. Ecurie is founded in 1999, and which makes us the second oldest Formula student team in Germany. And currently we have over 80 active members and over 400 alumni. And in the history of the club, we already built 10 combustion cars and 9 electric cars. In the front, on the right side, you can see Nuri, our 9th and most recent car. And on the left side, you can see Rita, the 7th electric car in the series, and which we have converted into a driverless car to take part in the competitions for the driverless cars. Here's a short overview about our team structure. We have the club board and 3 technical team leaders. The mechanical team leader and the electrical, and the third one is the administrative team leader. And then we are subdivided in 8 sub-teams, which operated underneath these team leaders. And so this way we can be sure that each department can specialize in its field and get the optimal performance out of this season. And the frame and the aerodynamics are the 2 groups which work mostly with the Altair software. There are some groups which work partly with it, but we are the groups which work the most time with the software. It makes our work a lot easier, and so we can achieve much better results. As I said, we are founded in 1999, and in 2002 we had our first job with our first combustion car, the EAC01. And then in 2010 We built our first electrical powered car and run the two classes parallel until 2013, where we built our last combustion car. And in 2017, we added the driverless software and sensors, cameras, all you need for a driverless car onto our 7th electric car to start competing in the driverless class, as I said. Here you can see the EAC09, the car where we take which one will take part in the events in this summer, the last month. It weighs 165 kilograms, has a full aerodynamic package, which means front wing, rear wing, under tray. Is a 4-wheel driven car, and the focus is completely on lightweight design to gain the optimal performance. On this slide, you can see the EAC is 07.D. Point D stands for driverless car. It's called Rita, as I said, and weighs 220 kilograms. And is driving with a LiDAR and 3 cameras, which we added on the top of the car on the main hoop. We also need a car PC with software, which we developed by ourselves. With this car we competed this summer. Also in Europe. Here are the results from the summer from the EV car. It was a really successful one for our team because we won the first time a competition overall in club history, the Formula Student Austria. And also we were always close to the podium on almost the others as well. And we had a great success also with the driverless car. We were able there to achieve the 3rd place in overall in Hungary, so in Formula Student East. And that's the whole thing is based on a lot of work and development in the past years. Also with the software from Altair, which I will present later, especially because when we do lightweight design, because the weight of the cars plays a big role in Formula Student, we want to keep it as low as possible because it's a sensitive parameter when we think about a car which can competitive with the other teams from other universities. So we do not achieve the low weight only because of the choice of material, but also with new geometries, lighter geometries, optimized geometries. But there I have an example later. The software we use is on the one hand there's EsaComp, where we use it for, I will explain it later. Mostly we use HyperMesh with the Solver OptiStruct, where we do all structural simulation with. But also Altair Inspire is very exciting for us because we can rebuild our topology optimization with it very well. The following slides, I would like to give you an overview and more detailed impressions of what we do with the software, what we have achieved with it and how our workflow looks like. Here, let's start with EsaComp. When we start to design a monocoque, we did the preliminary design with EsaComp. We simulate there a 3-point bending test because it's prescribed by the regulations we got from the FSG. For some years now, we've been using a sandwich structure in the monocoque, which means that there are a carbon outer layer, a core material, and an inner carbon layer. And that gives a lot of structure So, and at the same point, a lightweight design. And so in EsaComp, we can iteratively change the layers or the core materials, for example, aluminum, honeycomb, or the angle of the layers we want to lay in the panel. And so, yeah, we can click them fast together and simulate them also very fast. And then in the end, we can incorporate these results into the monocoque simulation, which you can see on this slide. Yeah, here you can see our current monocoque in Hypermesh. Yeah, after we had constructing it finally, we removed all detailed parts which are too complex, so it simplified the meshing very well. And yeah, then we declared some different zones in Hypermesh so that we can improve them locally more easily, because then we can assign a whole ply to the whole zone more quickly. And yeah, then in addition, we simulate the whole monocoque on a ply-based simulation and instead of a zone-based simulation. Yeah, that makes us having more freedom for our constructor in Hypermesh to play more around with some plies. Also, the main hoop and the front hoop are integrated into the simulation. They are simulated within 1D beam element. Yeah, with the corresponding material values from the steel we use for those two parts. Yeah, we integrate them because they are main parts of the monocoque, and they are stable them also quite much. Yeah, we also already we every time simulate our monocoque for torsional stiffness, which means that we fix the car in the back and torch them in the front. We are doing this because when we have a good torsional stiffness, which we simulate in the beginning, how much we need, we can be sure that there's also sufficiently present a good bending stiffness, so that we can set our setup quite well. And yeah, in addition, the suspension rods are modeled with tubes with our own material values, and the wheel hubs are infinitely stiff parts, and we use RBE2 elements to simulate the connections between the monocoque and the hardpoint, as you can see on the left picture. And yeah, then we are able to apply a force on the front axle on the one side and fix the monocoque in the rear completely, except one side in the movement in lateral direction. And yeah, the force in that direction isn't that important or relevant because we calculate the torsional stiffness later, linear elastic, and from this value we calculate our torsional stiffness. Here you can see simulation result from the monocoque simulation. You can see that the red part of the monocoque deviate a lot, or that means that there the monocoque has the most torsion. So then we can measure the displacement from the point where the force acts and calculate then our torsional stiffness. And after many iterations and a lot of simulations, we achieved our goal and had in the end a torsional stiffness which was greater than 5,500 Newton meter per degree. And it was somewhat higher than our target, so we were happy with it and decided to build or laminate this monocoque in this season. Another example of another part in the car which we designed with Hypermesh is the steering cage. It's right behind the dashboard and stores our steering. And yeah, here we were able to save a lot of weight due to the fact that we used the topology optimization. Yeah, after we printed then out the result out of aluminum. And here on the slide, you can see the installation space we gave the program and the corresponding bearings with their forces and yeah, the forces which the simulation should take into account. And we determined these forces before, and so that we got a realistic simulations for our steering cage. And after a simulation, or after some simulation, we got this result. Yeah, it's always exciting to see those results from topology optimization, because you can learn a lot about the load paths from these different forces, and yeah, also for different materials when you tried it out. Yeah, it looks every time a little bit different. And so yeah, this was our result from for the steering cage, and here you can see now where we began to reconstruct our result from the simulation. We did this in Altair Inspire, and yeah, tried to do it as closely as possible to the simulation result. It took a lot of time, but with the result, yeah, was quite nice. And after we constructed, finally, we go back to Hypermesh and simulate the constructed part with the assumed forces and the same connections as the topology optimization. So yeah, that we get then an idea of how the construction works, and maybe yeah, maybe we can save somewhere some material to save some more weight. So it was an iterative loop of a simulation of the result, and interpret then the results and remove some material and simulate them again until we have a final result where we could save 30% of weight compared to our old concept, which was a welded aluminum cage behind the dashboard. So yeah, quite a lot when we think about this small part. Here you can see the final printed result, including the built-in steering, as it is also installed in our current car. Yeah, and on the right side, you can see how the printed parts comes from the manufacturer, still having the support structure inside, which we have to remove and yeah, make some different things with it before we could install it into our car. Yeah, then I have another assembly group which were designed with Hypermesh, the Aerodynamics. So we simulate all structural things for the Aerodynamics Hypermesh. After we retrieve the geometries from the Aerodynamics group, we can simulate the layup and the inner structure for those parts. We calculate on the one hand with the aerodynamic load, and on the other hand with the loads from the regulations. For example, every aerodynamic part is allowed only to displace 10 millimeters while acting 200 Newton on a surface of 225 square centimeters. And yeah, here you can see the whole rearing in the simulation, but also some individual flaps for some individual simulations to become a more precise result. Yeah, and with this concept, we simulate every aerodynamic flap and try to get them as stiff as possible with the lowest weight. before we start to manufacture them. And another example is the Frontwing. Here you can see the main element. Yeah, it includes a lot of points where the force acts. Yeah, we did this because we want to be sure that at every point the wheels are or the part is fine with the wheels. And here at the green part of the main element, the flap were completely fixed in all directions, as it is later in the monocoque. So that we had a realistic simulation as possible, so that we can be sure that the front wing we built then later is rules compliant too. So yeah, here you can see in the next slide the result from the simulation. It's a result from the force acting most outward. So yeah, it has there was the most displacement, obviously, because of the largest lever arm. And yeah, after every simulation, we can see if it makes sense to add some more layers of carbon, maybe some UD stripes to support the structure, and or some different inner structures. And yeah, in this way, we did many simulations for every part to get the best layup for our structures. But for us, there's not only the displacement interesting, also the composite failure of the layup, because when they had too much stress, then they got they fail, and that would be not that good, of course. And yeah, that's also something we have to take into account, that all our fibers are still working under the loads we have in our races. Here's also the example, the Frontwing main element on the top and on the bottom side. There are different places where the composite failure is bigger, and where you could think about to add some more plies, to have a bigger safety factor. And then this was my presentation about the work with the Altair software in our Formula student team. I hope you got a good insight into our work and enjoyed my presentation. I want to thank you for your attention, and I'm available for further questions under the contact details shown onto the slide. Feel free to contact me there. Also, many thanks to Mr. Grasmansdorf to giving us the opportunity to make a presentation here and share our results with with some people who are interested into it. And yeah, I want to say goodbye, and I hope you have fun in the workshop.